Level curves of a potential function are called equipotential curves. That's curves where the potential function is constant. So remember, we've got a potential function phi. When you find the gradient of phi, you've defined a vector field f. Okay, so phi is that scalar valued function. Level curves of phi will be when we're letting phi be constant values. So we're going to draw the level curves of phi, which are denoted here in the green. Remember that gradients are orthogonal to level curves. So if we're trying to graph this vector field, the vector field is made up of gradients of that potential function. So the gradient will be orthogonal to the level curve. So the gradient, which is the um, representing the flow of these vectors in the vector field, will be orthogonal to all those level curves. And the level curves are called equipotential curves. So all these in green are equipotential curves. Each one represent a constant value for the function phi. And if we were to draw the vector fields at each place where it's crossing a level curve, it has to be orthogonal at that point. So it'll come along to another one and it's got to hit it where it's orthogonal. So when it crosses that level curve, it's got to be orthogonal. So by starting to draw a curve and just making sure that you're always orthogonal to the curve, the level curves, you get one of these curves, the flows from the vector field. So we can see what the vector field is going to look like here by looking at these flows going across the level curves. So I know if I were to go this way, I've got to go orthogonal there, but then when I get to here, I've got to go orthogonal. It's going to come along and it's got to be orthogonal here and it's got to be orthogonal here. So I can get what the flow of these vector fields is by just seeing the level curves and making sure the gradients are orthogonal to it. Okay, so let's look at a specific function. Equipotential curves for this potential function are shown in this graph. Now, if we were to find the equipotential functions, which are just the level curves are letting a constant value be in place of the phi. So if I use the letter c to represent that constant value, I get x squared over 2 minus y squared over 2 equal to c. And if you recognize that as a hyperbola, you can see that the level curves for this potential function are hyperbolas. So you can see in the drawing down here that we've got various level curves. So here's one hyperbola and here's another one. Okay, or if we have the other ones going in this direction. So the potential function phi has level curves that are these hyperbolas in the graph. So now let's look at the gradient. We want to find the gradient field that's associated with phi. Well, the gradient of phi will be the partial derivatives with respect to x and y in the two components in the vector field. So rewriting the phi in this way, x squared over 2 minus y squared over 2, we see that the gradient or the vector field would be x comma negative y. Okay, so that's the vector field denoted by the gradient generated by this potential function phi. So now, the gradient field we want to show is orthogonal to the equipotential curve at 2, 1. Well, let's look at the equipotential curve. This is one equipotential curve. Okay, if you want the equipotential curve at the point 2, 1, we can find out what that phi value is. So phi at 2, 1 would be 4 minus 1 over 2, which is 3/2. So it doesn't make a whole lot of difference, but the particular level curve at 2, 1 would be x squared over 2 minus y squared over 2 equal to 3/2. Okay, now if you remember how to find the derivative of a function, a multivariable function, I want to find the derivative of this function. The derivative, which is dy dx can be found using a formula that we got back in section 13.5. To find the derivative dy dx without having to use implicit differentiation, you would take the partial of this function, I'll just call this function f, take the partial of that function f with respect to x over the partial with respect to y and make it negative. So finding that partial with respect to x of this function would just be x. So I've got the negative x on the top, and then the partial with respect to y is negative y. So x over y is the slope of the tangent line of the level curves or equal potential curves. Okay, so now what I want to do though is I want to show that that tangent line is actually orthogonal to the gradient field. And here's our gradient field. So I've got a slope given as a fraction and I've got a vector. So let's make both of them vectors so that we can then see if they're orthogonal by doing a dot product. You could also take that vector x minus y and change that into a slope. And then remember that two lines are going to be orthogonal or perpendicular if they have negative reciprocals. So let's just change this though to a vector. So a line that had a slope of x over y means that you're rising x units and you're running y units. So that vector that's represented there would be the vector ending at that point, which would be the point y comma x. So this would be a vector y comma x. So if you had a line that had a slope of x over y, then it would be parallel to the vector y comma x. So now take the vector y comma x, which is representative of the tangent line slope for the level curve, and take the dot product of that with the vector field, which is x minus y, and you get xy minus xy is equal to 0. So that shows that the gradient field associated with phi is orthogonal to the level curve at 2, 1. Okay, so now actually we just showed it for any point xy. We didn't show it for a specific one. So we actually just did part B. Now let's go back and do part A. For a specific point 2, 1, what's the slope of the tangent line? Well, dy dx evaluated at 2, 1 would equal to x over y, which is 2 over 1. So that's a slope of 2. Okay, so now what's the gradient at that point? The gradient of phi at 2, 1, which is x minus y, evaluated at 2, 1, would be equal to the vector 2 comma negative 1. So now again, we can either look at this as a slope or we can change a slope into a vector. Changing the slope into a vector, we would think, okay, a slope of 2 up 2 and over 1 would be the vector 1, 2. So 1, 2 dotted with 2, negative 1 again gives us 0. Now if we wanted to do, just to give you another way to look at this, if you want to take this gradient and say, okay, that's represented by the vector 2, negative 1, the slope of that, you know, the line that would be passing through that would actually be, let's see, rise would be negative 1 over run, which is 2. So negative 1/2 would be that slope. And then looking at this slope and this slope, which is the slope of the tangent line, they are negative reciprocals, which also proves that they're orthogonal to each other.